Hey guys, let's talk about work and energy here. A couple definitions for you and everything, but first up, I want you to know that energy enables work and work produces energy. Okay? They're kind of the two sides of the same coin. If I have energy, I can get some work done. If I do some work, sometimes you can generate some energy out of that. So we'll see how all that works. Here are the definitions, the things I really want you to know about about these things. So we've got some formulas, that I'm going to circle up here and get you to think about with this. The first formula I'd like you to know is that work equals force times distance. When I push on a box with some amount of force and move that, I have done some work. I have changed the physical position of that thing, and that change of position is what we call work. It gets measured in joules. Think about what's happening here. It says up top that 1 Newton meter is 1 joule. So you know how we measure force in newtons. We talked all about force last week. And you know that distance gets measured in meters. So multiply Newton times meters, you get this new unit called a joule. Now, if you boil that down, you remember that a Newton was really a kilogram meter per second squared. And here I'm multiplying one more meter. So you see how I've got a kilogram. I've got a meter times a meter, or a meter squared, and there's a second squared on the bottom. So that's really the units there. We don't want to write all that mess, so we just say, hey, let's name it after James Prescott Joule, this guy that measured a whole bunch of energy stuff. And so that's why it's named that way. The kinetic energy is the energy of a moving object. Anytime I throw a baseball, then that moving object took energy to get started. I had to put the energy in it from my arm into the ball to make it go. And if it goes and hits a window, then that energy is going to transfer from the ball to the window and we'll probably break it, right? It has energy. Every moving object has energy. So the little formula for that would be the kinetic energy equals 1/2 mv squared. And believe it or not, that also gets measured in joules. All of these forms of work and energy get measured in joules because they're all kind of variants of the same thing, and we can transform from one into the other. Right here, the potential energy. This is also known as the gravitational potential energy. Probably should say that right there. But if I do some work to raise a box of books up in the air, that work that I did gets stored in there as potential energy. So I'd kind of like you to think of this as stored energy. Sometimes you'll see it's energy by virtue of position. Like, for example, if I compress a spring, I'm doing work to mash that spring in tighter and tighter, and that work that I did has to go somewhere. The energy that I used has to go somewhere. It goes into the spring. It's stored there in the spring, and then I could release that energy and make something become kinetic, make a dart go across the room with a little dart gun or something. All right, so that's a good formula, and I've got examples of all these coming up pretty soon. Heat is a form of energy. I don't really have a formula here for you, but we use the letter Q for that, and guess what? It's also measured in joules. The oddball here is power. Power is either work divided by time or energy divided by time. Since work and energy are kind of the same thing, different variations of the same thing, then I could switch back and forth there. But it's either how fast am I doing work or how fast am I using energy. So that's a useful formula too, and I would circle those up. This one you could see that I'd have joules of energy on top and seconds on the bottom, and joule per second seems like a lot to write, so we call that watts. If you look on the top of a light bulb, it says 100 watts, right? That's the unit that we're talking about right here. And James Watt invented the steam engine. He was instrumental in moving us into the industrial age, and when we think about changing our life, James Watt and having a machine, a motor that did work for us instead of us standing there poking holes in the ground and dropping seeds in, we can jump in our car and go to town. That's kind of a big deal, so they named the unit after him. All right, here are those examples I promised you. Find the work to lift a 30-kilogram box into the air. So as soon as I see the work right there, that word work, I'm going to go ahead and write down work equals force times distance. As soon as I see potential energy, I've got a formula for that. Potential energy, and this is gravitational potential energy, mgh. Here's kinetic energy. See how you're just using those definitions, those formulas, to get started on this? So this is a possibility where they just say, well, go find the work, go find the potential energy or something. Sometimes it still takes a little bit of head scratching. Here is a box, 30-kilogram box. It's on the ground. I want to raise it up into the air, and so I need to know how much force it takes to do that. From what we did last time, remember that gravity pulls down with mg. Weight is mass times gravity. So that's the force that it's going to take to lift this box up. And the height that I'm going to raise it is x, or I could call that h, either way. And see, there's that mgh. The work that I do to raise it up in the air is the same as the potential energy once I get it up there. It has to be. Where would, it's not like I'm going to make extra energy out of nothing, right? I raise a box of books in the air and all of a sudden there's more energy than I started with. That doesn't make any sense. It has to be the same number. So all we really have to do here is take the 30 kilograms of mass, multiplied by g, 9.8 meters per second squared, times h, the height, the x, whatever you want to call it, but 6 meters right there. And that's going to be some kind of number. 30 times 9.8 times 6 is 1,764 joules. We're measuring energy, so it's in joules. If you want to see it happen, I got a kilogram meter per second squared times a meter. This makes a Newton, like we had last time in force. So I got a Newton times a meter, and that's a joule. Works out nice. Okay, right here I'm trying to do the potential energy of a 30-kilogram box at 6 meters in the air. mgh, that's the calculation we just did. So I could run these numbers again, but I don't really need to. It's 1,764 joules right there. The work that I do to get it up there is equal to that stored energy once it is up there. And now, check this right here. If I were to drop that box from here down to the bottom, how much kinetic energy would it have right there when it hit the ground? Well, I'd have to do 1/2 mv squared. It's a 30-kilogram box. I need to know how fast it's moving. If I drop it, then the initial velocity is 0. I'd like to know the final velocity. The acceleration is g, 9.8 meters per second squared, and it's going to fall a distance of 6 meters. I could use kinematics, right? Here are those variables. I could plug it into v squared equals v naught squared plus 2ax like we did on the first section. Put your numbers in. The velocity when that hits the ground can be 10.844 meters per second. It says I have to square that right there. It's so easy to lose that little squared, so watch out for that. But here I could come along and go 0.5, that's the 1/2, times 30 times 10.844 squared, and there's my 1764 joules again. It's still all there. It has to be. Where would it go? Where would I get more? It has to be the same number all the way around. So we did some work to raise a box. We calculated how much potential energy it had up there. We dropped it, and just before it hit the ground, it had that same amount of energy. It's always the same number. And in fact, we could come in here and say, well, what about smack dab in the middle? Right there, I've still got some height to fall. In that case, I have some potential energy, and it's also moving. When it gets halfway down, it's moving, not as fast as it is at the bottom, but it's got some of that kinetic energy. And when I add those two together, I'm going to get I'm still going to get this 1764. You can pick any point along the path that you want. It's still that same amount of energy, because where am I going to get more from? Where am I going to lose it to? This is a big idea in physics, and it's what we call the conservation of energy. The energy at point 1 has got to equal the energy at point 2. Sometimes I compare this to money. If I take my wallet out of my pants pocket and I open it up and I look in there, there's not going to be any money in there, okay, because that's the way it works. But let's pretend there's $10 in there, and I close it up and I open it again. There's still $10 and $10. Every time I look, there's the same amount of cash in there. If I go to the grocery store and I buy $2 of apples, now I have $8 worth of cash. Started with $10. Now I have $8 of cash, and I've got $2 worth of apples. And see how it still adds up to 10? No matter what I do, I can't open my wallet and all of a sudden there's $40 in there when I didn't put it in there or earn it or do something. There's no free lunch in the universe. This energy is conserved. It's the same number throughout. If I want to put more money in my wallet, then I've got to go do some work. And me doing that work converts into money in the same way work converts into energy here. So that's a possibility. Usually when we do these conservation of energy problems, we're talking about something like a roller coaster. Now, I don't know if you like roller coasters or not. I'm not a big fan, but let's say there's somebody in a roller coaster car here, and they're going to roll down the hill and then back up the other side like that. What we're saying is here's 3 different points, and maybe even all the way over here on the ground when the thing comes to a stop. At all 4 of those points, the energy has got to be the same number. Because where is it going to get more, right? Up here at the top, I've got a lot of potential energy because I'm way up high off the ground, remember MGH, and a little bit of kinetic energy. When I add those together, it's going to be equal to the total here and the total here and the total here. So that's what we're talking about. You pick any 2 of these points that you want, and that sum has got to be the same. The kinetic energy at point 1 plus the potential energy at point 1 is going to be the same as the kinetic at point 2 plus the potential at point 2. And if I break that down, here's how I calculate kinetic energy. I've got that little 1 to say at point 1, and the potential energy at point 1. Here is the kinetic at point 2 plus the potential at point 2. This is the form that we usually think of with with conservation of energy. It can go other places. It could go into heat, right? If I had friction in the bearings of the wheels, then some of that kinetic energy would be converted into heat. But normally we don't worry about that. We just pretend like the wheels are perfectly non-frictionless and or non-frictionless. They are frictionless, and so we don't worry about the other forms. It's just kinetic and potential. If you see a conservation of energy problem like the ones I have coming up right now, you can just write that down. And 9 times out of 10, if you're not considering heat or other forms, see how I've got mass in every term? I could factor it out of these guys, factor it out of these guys, and then cancel those. So you can just even knock the masses out like that. Now there's places you wouldn't want to do that, but for us, that's good enough. Here's a roller coaster, and they give me some numbers. 2 meters per second at the top of I'm going to have to move my little box here. Look at that. 24-meter hill. So they gave me the height and the speed at one point, and then they want the speed at a different height. I'm going to draw a little picture. You know me. Got to draw a picture. There's point 1 up there. My velocity is 2 meters per second. So that'd be V1. H1 is 24 meters up. and then a little bit above the ground, let's say about here, not quite all the way down, but V2, the speed down there is what I'm after, and H2 is 3 meters. Okay? So that's my problem. And this is so easy because I don't have to go back to kinematics and forces and all that. I just use conservation of energy. The energy at point 1 has got to be equal to the energy at point 2 because the universe doesn't hand out free energy. That thing that we wrote out before was 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2. Like we said, we can cancel out all these m's because it's in each and every term. Don't have to worry about that. I don't have the mass of the roller coaster. I don't need it. All right. Let's just check off, though, what we need and what we know. I have V1 and H1, and I have H2. I'm looking for V2. See how I've got all of the variables except for one, so I need a little bit of algebra here. And what we're going to do is the same algebra we've been doing all the time. Here's some addition stuff, so I'm going to get rid of that first. I'm going to subtract GH2 from both sides. That'll knock that thing off. Let's see where that leaves us. I've got 1/2 V1 squared plus GH1 minus GH2. Make sure you get this guy and that guy on the left, and then I've got 1/2 V2 squared on the right. Now I'm still not done. You can see right here that I need to get rid of that 1/2. The easiest way to do that is to multiply by 2. And the 2 times the 1/2, the 2 on the top would cancel the 2 on the bottom. I'm just multiplying by 1. So that's gone, but I've got to do it to the other side. And I want to make sure that everybody gets their fair dose of 2. So I'm going to put some parentheses there to do that. Now you could distribute here if you wanted to. Take 2 times the first and the second, third. But I'm going to just leave it like that. There's one more thing we need to do. Now that I've got 2 times 1/2 V1 squared plus GH1 minus GH2, that's equal to V2 squared. I don't want V2 squared, I want V2. So I got to get rid of the squared, and the opposite would be the square root. If I take the square root of the right-hand side, the square root and the squared will cancel each other. That means I got to do that over here on the left-hand side too. All right, looks like that. Looks like a big mess, but all you're going to do is plug some numbers into it. So fear not, it's going to be okay. Here's a 2. That's outside. 1/2 V1 was, I've got it right here in my picture. I don't have to go searching in the problem anymore. Times 2. And it would be good to put the units here. Notice that has to be squared. Plus G is 9.8 meter per second squared times the height up at the top. Point 1 was 24 meters minus 9.8 meter per second squared times H2. The second height, the lower height, is 3 meters right there. Now the beauty of this process, I'm going to get my calculator and see what this is because I'm dying to know. But secret is anything that you do like this where you have a single object at 2 points, all you got to do is do conservation of energy. So let me get you a number here, 9.8 times 3. All right, notice I've got that square root over the whole thing. It started a parenthesis there for me. I've got the 2, which was outside, that 2, which is outside all this parentheses. So there's another parenthesis. There's my kinetic energy term with the mass canceled out, and the potential at the top minus potential at the bottom, again with the mass gone. I could close both those off if I wanted to, but you don't have to do those. I've got a number here, 20.4 I'm going to put. And if I went through this, this would all work out to meters per second. Okay? I don't know that you need to do that, but here's a meter which gets squared and a second which gets squared, and then I'm taking the square root of it, so that would be meters per second. Here's a meter. Meter would be a meter squared over second squared, square root meters per second, and so forth. Okay, so it does work out, and that is the answer. That's the speed that our roller coaster would be moving after it dropped from 24 meters to 3 meters if it was moving 2 meters per second at the beginning of all that. All right, and that's pretty straightforward. This is a general rule here. If you see one object at 2 points, if you can draw a picture and the roller coaster car is here and later on it's here, it's a conservation of energy problem, and you know exactly what to do with it. There's a little bit of algebra here involved and getting the right variable, but just do it like you always would and you'll be fine. Okay, here's a couple more. I don't know that we need to do all these, but if I take an arrow and I shoot this thing up into the sky, now it's up here. Can you see that it's at point 1 and at point 2? What do I do with it? Conservation of energy. It's one object at 2 points. Here I have a hammer, and I'm going to drop it, and it's going to fall down 40 meters. You see the point 1, point 2? It's a conservation of energy problem. And you know exactly where to go with that. And so that's good stuff. All right. Got one more idea here for you. This is called the work energy theorem. And you remember how work and energy were the two sides of the same coin and could flip back and forth all the time on you. If I do some work, it changes the energy that I have. Or alternatively, if I change the energy, it can go into work. For example, you put gasoline in your car, you've got all that energy there, and when I burn some of that energy, that changes the amount of energy I have available, and it puts that into the work of the car. So a lot of times you'll see problems where there's a car moving, and they ask for how fast it's going at the end or something. I think I have one here. Yeah, let's give this a try. Here's a 1,200 kilogram car. It's moving on level ground. That's enough for a picture right there. So here's my car. I bet some of you are wondering what kind of car that is. You wish you knew, didn't you? So you could go buy one. They tell me the mass, 1,200 kilograms, and it starts out moving 16 meters per second, and it goes to 5 meters per second. I'm going to put the initial velocity is 16 meters per second. The final velocity is 5 meters per second. Can you see that's going to have a different kinetic energy at the beginning and the end? How do I change energy? I thought energy had to be conserved. Well, it does have to be conserved. We're just moving it from one place to another. What's going to happen here is I'm going to step on the brakes, and the brakes are going to get hot. All right? You go down a big enough mountain with enough of a load, your brakes catch on fire, right? There's that much heat. That energy has to go somewhere, so it slips off into another form called heat. That's like buying the apples, right? It's still there, but it's in a different form now. So when I lose all this kinetic energy, that's going to make a good deal of heat. Now, what they want to know is the average force. And they also give me the distance here. So all along this way, I'm standing on the brake pedal, trying to get my car stopped. I'd like to know what force the brakes are putting on the car, and they also gave me the distance is 250 meters. Okay, well, right here, as soon as I see force and distance, that immediately makes me think of work. Force times distance is work. And I see that change of kinetic energy. So I'm thinking about the change of energy on that. And that's that work energy theorem. Okay, it has to add up, but we change this number. That means I changed this number too, right? That I did some work there, or the brakes did some work in this case. So here's kind of the stretched out version of this now. This is only the final kinetic energy and the initial kinetic energy. It doesn't include the possibility that we were also going uphill or that the brakes were getting hot or anything like that. It's just the change of kinetic energy and sending all of that into the work that the brakes did. But I'm going to use that one. That's good enough for what we're doing right now. So that would look like this. And I know that work is really force times distance, isn't it? So I could even come in here and take that work and rewrite that as force times distance. Force is what I wanted. I have the distance, I have the mass and the two velocities. So see how if I just divide both sides by x, then I would have that force by itself. Set it up so the x cancels, there's force, and then I'd have to divide all this by x. So that's my game plan here. Let's see what happens. I've got 1/2 times the mass. The final velocity, v, over here is 5 meters per second. That has to be squared because the formula says so. Okay, minus 1/2 times the mass, 1,200 kilograms, times the initial velocity was 16 meters per second. And that has to be squared, and I'm dividing the whole thing by the distance of 250 meters. All right, we're going to grab our calculator and get a number for this, but that's a pretty good illustration of the work energy theorem. I have a change in velocity. I'd like to know how much force or distance I have. One last thing before I get to moving on this too much. I've got all this addition subtraction on top. Let's make sure that happens before the division. So let's start the parenthesis off. I've got 0.5 times 1,200 times 5 squared minus 0.5 times 1,200 times 16 squared. I think you can see this is already going to come up a negative right there. I'm going to divide by 250, and there's negative 554 joules. Wait a minute, I'm sorry, we're looking for a force. Negative 554.4, it's a force, so it's a Newton. This would all be in joules, and I divide by meters, and I'm going to end up with a Newton there. Okay? So that's the force that the brakes have to put on the car to slow it down. And if your car can't provide that much force, then you're not going to stop. You're not going to slow down, right? Why is it negative? Because my car is moving this way. That's the positive direction, and that force is acting backwards, slowing it down, almost like you threw a parachute out or something, and that parachute's pulling you back, slowing you down. So that's why it's a negative number right there. Okay, if you were speeding up, it would have been a positive force like that. All right, here's the little summary. Everything you need to know. You got the formulas for work and kinetic energy and potential energy and power. Down here, you know that conservation of energy always works in any closed system. If you have one object at 2 points, then you're good to go. It's conservation of energy time. All right, and then lastly, that work energy theorem is real handy whenever you, especially if you see a change of velocity and they start talking about work. Remember that work is force times distance, so if they give you the force and the distance or ask for one of those, probably want to go with work energy theorem there too. So that's what I'd like you to know about kinetic energy, potential energy, work energy. I didn't do a power, but you could see where that would work out. Thanks for stopping by. Have a great day. Let me know what kind of questions you have, and we'll figure all this stuff out. Thanks.